So I want to determine stable versus unstable nuclei. And the way we do that is that we compare binding energy versus electrical energy. And we talked about our atoms. We're not interested in the extremely unstable atoms that nobody will ever observe. That's 109 to 118. We're talking about the ones that we actually observe. So we should list them in terms of three categories. There's the atoms. Okay, so there's the atoms. Okay, if I could get started here. Atoms 1 through 82. So this is hydrogen to lead. So this is a very important category, of course, because this is what we observe. So what do we know? We know that stable nuclei last forever. And what does that mean? What that means here is that when I look at the attractive binding energy of the strong force, it's much larger than the repulsive electrical energy from the protons. So if I draw a picture of this, what does this mean? Well, I have a bar. Let's say that this is the bar, and I look at this binding energy, and what I'm going to do here is that now I compare this to the electrical. And when I look at the electrical, it turns out to be quite small. So I look at the difference of these and I see, wow, there's a big difference between these two. So what does that mean? Well, what that means here is that I got to go in and go get the band of stability. So when I look at the band of stability, I know this is quite small, but we don't really need the numbers so much. When you look at the band of stability, what this really tells us here is it says this. These nuclei land on the black band of stability. So these are the stable isotopes, in other words. That's what that graph is telling us right there. And so what you're seeing here is that we should be a little bit more careful. Maybe I will make this a little bit bigger here. So when I look at this thing, the important number here is that 82. So where is 82? Well, it turns out it has to be right here at the end. So if you look at this number right here, the very last atoms should be 82. Okay? That's what we mean. So you could see here is that this is R1 and this is our 82. This is lead. And then this is, of course, hydrogen. That's what that graph. Anything beyond this has to be unstable and can't be in that black band. Now, unfortunately, this graph, you know what, my line is not even straight. This graph is not absolutely correct. It's not scaled right. Okay, it's not scaled right. And if you look, all the squares are jagged and, close up, and there's a problem. So it looks like it's beyond 82. It's not. because the last atom that's stable is lead. Now, let's go to the next one. So the next group that we look at atoms 83 through 92. And this is an important group here. So these guys are the unstable nuclei on the table. In other words, 83 bismuth is the first unstable atom. And we'll talk about that more in a little bit. So these are unstable nuclei that naturally exist on Earth, but have no stable isotopes. For example, if you look at lead 82, it has 3 stable isotopes, 206, 207, 208, and they live forever. So the question is, why is it that these guys are unstable? And what you're finding here is that it looks something like this, is that when I look at the binding energy looks something like this. And what you're finding here is that the electrical energy is slightly less. Okay, so it's slightly less. So when I compare these two, what we're seeing here is that the nuclear binding energy is slightly more than the electrical repulsive energy. And so what you would see here is that where would these guys land? So if I was to take this table here, or this graph, and I was to paste it right here, where do they land? It turns out that these guys are not shown here. So if we had scaled this properly, this thing right here would be at 82. Okay, so this is the number 82. It looks like it's higher. So what you would see here is that now the band continues, but this doesn't show it here. So if I look at this thing, the band continues like this. And what you would see here is that then this thing ends where? If we set this scaled right, this thing right here would end at, that number there would be 93. So you're seeing a very small area where these guys exist here. So let me try to extend this a little bit more, see if I can. So what you would see here is that when I look at that little piece of the band right here, right in here, these guys are atoms 83 to 92. And what you would find here is that these, how do I say that? These nuclei do not land on the black band, but live on the yellow band. They live on the yellow band. And so what happens here is that you start to see some very interesting results here. So if you were to look at uranium, let's look at uranium. So if you look at uranium, uranium is unstable. So let's say that uranium would be right here. Oh, I don't want to draw that with the black dot. Okay, let's draw it with the purple. So let's say that this guy right here is uranium, right? And then this guy right here, this guy is bismuth. So what you find here is that uranium and bismuth have a tendency to be more in the middle of the line, of the yellow line. And as you get towards the edges, you get more and more unstable. And so this brings us to the next atoms. So these are atoms 93 to 108. Some of these atoms can have quite a long lifetime, and some of these atoms can be extremely unstable. So it really depends on what. Again, it's the binding energy versus the electrical energy. By the way, I should have drawn this line here so you could see that there was a difference in height. Now, here we go. These guys are highly unstable. Nuclei and have slightly smaller nuclear binding energy than electrical repulsive energy. So when I look at this here, the binding energy is now slightly smaller. So if I'm comparing these guys, you're seeing that this guy is slightly bigger. So if I look at the band here, not the band, excuse me, the height of these, you can see the difference between these two. And so these atoms, what we say here is that these do not exist naturally on Earth, but must be manufactured in nuclear accelerators. And one of the clearest example of this is plutonium. Plutonium is then, you can use either a combination of a reactor and an accelerator, and what you do here is that you literally start making it. And what it does here is that it then forms a metastable state. That if early in the Earth you had some plutonium in the ground, by the time the age of the Earth has come to 4.5 billion years, all of the elements 93 and above have already decayed out. Why? Because the electrical energy is slightly greater than the binding energy, and that does it to that.